I can write this. I didn't know it till now. I can write that. There is a potential function that exists where these are the partial derivatives. Cool? Alright. By the way, the author does not write this, and that's okay. You know what the author does? The author called, you might find this easier when I show you something. You see how I wrote this so far? See my notation? What was I doing? I was doing, stuff from, remember we did max and mins and stuff? With the fxy and the fy-axis? I wanted you to see it. This is something from a previous lesson. Well, the author, because these are not, we're not sure if these really exist yet, the author just calls this component P, and he calls this component Q, and he says, what you got to check is, he goes, you just got to check that the derivative of the P with respect to a what? A Y must be equal to the derivative of the Q component with respect to a X. Do you follow me? But he's really just looking at Clairaut's theorem. Do you follow me? Does that make sense? He's really just doing Clairaut's theorem. So if you want to write it like that, it's totally fine. Your P, your Q, is dP dy equals dQ dx. And these are really deltas because they're partial derivatives, right? I should really write them as deltas. Delta P, delta Y, because they're partial derivatives. If that's true, then it's a conservative vector. Alright, so when we agree this is a conservative vector field, this is equal to del F, or the gradient of F. By the way, that's the other notation, remember this? GRAD of F? That exists. So now, this is going to be an easy problem. But to do it, what is it equal to? This vector field is conservative. So I can do this. And I'll just go from one endpoint to the next endpoint. And what do I do? F of endpoint minus the F of the initial point. But don't get confused on the test. I mean, this is going to be a fast problem. I'm bypassing doing all the antiderivative work and the dot product. I'm not doing the dot product. What's that? How do I get this potential F? We got to do that. So do you remember how to do this? How do I get, I'm going to draw an up arrow, get the P and Q out of the way, and here we go. What is that potential function of X and Y? Remember how to do this? Integrate this with respect to the letter X, put a plus. Integrate this with respect to the letter Y, and if you get any repeats, just toss out the repeat. Maybe let me show you this in a minute. It's a cube, that's a square. What's the integral of that? With respect to X.
1/3 x cubed y cubed.
X cubed y cubed over 3.
Yeah.
Outstanding. Plus, now integrate this
X.
with respect to y. It's a partial integral. And integrate that with respect to the letter y.
Same thing.
Same thing. So do I leave both of them? Do I add them together?
No. Just figure
Toss out any one.
repeat.
Yep, so I'm going to write down, if you can, sometimes it helps when you, even in your notes, because you'll go back and look at this a week from now and go, why did I toss it out? I'm going to write, this was a repeat of the same expression there, so we'll just go, we don't count you twice. And you would notice the derivative wouldn't work out anyways. Oh, and should I put the plus constant? Plus constant. There's the potential function. All right, now, what's this answer? Get F of endpoint minus F endpoint. Let's see, there's F. Are you serious? All I have to do to work this problem is right there, put in the endpoint and the initial point and subtract. That's all I got to do. But there's one catch. They said go from t equals 1 to
T.
t equals 0. Ugh, this has what letters?
X.
X and Y. So and here's the big secret. I don't want this to stump you on the test. I'm definitely going to plug some numbers in here. I'll put them there, and I'll put them there. But what are the X and Y's when T is 0? And what are the X and Y's when T is 1? So can you help me out? I encourage you to make your own little table. Here, right on the test, go. This is going to be, let's call it my table. Make your little table, and you know what you're going to put in there? A row for T, and a row for X, and a row for Y. This is the mystery. And it can stump you during a test, because you will sit there, it can confuse you. You could sit there and go, I know I just got to put this right here, and right there, and subtract them, but I don't know what numbers to plug in there. And this looks messy, right? This looks completely messy. So let's go figure it out. What are the t values?
0 to
0 to 1. How can I find the x's and y's? I know you know.
Yeah, just
They're right there. That's the x. See, that's what's missing. That's the x component, right? That's the y component. Let's start. What's going on at 0? What's 0 minus 0?
0.
0. What's, there's a y component. What's 0 plus 2 times 0? So I got you. T equal to 0, x is 0, and y is 0. What's going on at t equal to 1?
Negative 1.
1 minus 2 is negative 1. Very good. What about at 1 for the y component?
3.
No one problem? So now guess what we'll do? Here, we'll do it x cubed, y cubed over 3. X cubed, y cubed over 3. Do I have to put the plus k's? What happens on a definite interval? Those constants just do what? They would subtract out. Do you agree? Remember there was a plus k here? They'll just subtract out. It's a definite interval. We're doing this now. What's the values we're going from? We're going from 0 to 1, but we define them right there. So let's plug them in. Now don't be like me on a test. Oh, I remember this as a student. I'll never forget this. I flip-flop these. Make sure, which one's the endpoint? What do they mean by endpoint? Is the 0 the endpoint? When I'm saying an endpoint, I mean this point. It was like a path. Something moved up, this C is a curve, and it moved along a path from t equals 0 to a t equals 1. The endpoint was what?
1.
T equals 1. The initial point was t equals 0. So when they write it like this, just remember that. This is the endpoint. And it's endpoint minus, I just didn't want you to get the opposite sign. All right, let me go, here we go. What's negative 1 cubed times 3 cubed over 3? And I need you to subtract. Oh, this is easy. What's 0 cubed over 3? What's the final answer? Negative 9. And did this find something in real life? You go, yes, this just found the work. This was the work done by the vector field to move a particle along that curve from that point to that point. That's what it did. But when you see what's so great about this section, in the end, I don't have much writing on the board. If you and I did that dot product, my goodness, it would have been drastic, right? That's what's so cool about this. So now the key is, with this section, when you hear FTLI, fundamental theme line integrals, please think it's all about whether or not the vector field's conservative or not. Now what if this vector field wasn't conservative? I'm sorry, I would just have to do it directly. The F dot dr, I would have to do F dot, the R prime ddt. Cool. Awesome. Hey, something else about this. This is pretty cool. There's another theorem. I didn't write it on the board. But will you put this in your notes? Line integrals of conservative vector fields. This was a conservative vector field, right? Line integrals of conservative vector fields are independent of path. This means it doesn't matter what path you take to go from one point to another point. See the 2 points? What's one of the points? I'm going to plot these. And this is the x, y, where's that point? 0, 0, where's this point? I'm going to go over 1 and then what? So in the path, went from here to there, right? If your vector field's conservative, we took this curve right here, right? You could have gone, you could take a path like this. This is going to be the curve C. It could be a straight line. It could have been a zigzag. It could have been a little loop like that. It could have been a loop like this. Any of these paths you could take, right? And you'd still get the same answer. And you go, why? If the vector, because hidden behind this is some vector field. This only exists for conservative vector fields. All right? So, line integrals of conservative vector fields are independent of path. It means it does not depend on what path you take to go from one point to the next one. Cool? Cool. Hey, this only takes a second. I wanted to show you an image out of the book. It's quite similar. If you want to work out the entire problem again, it's quite similar to this. Section 16.3. Oh, my integrals. Can I erase that? Okay, cool. Let's see if it's coming in. Yay! The problem, everyone, is number 11. Zoom a little bit. Zoom, zoom. Number 11. This is number 11. Not from our practice problems. This is textbook. So I'm like, the textbook every once in a while has a pretty cool problem. And I'm going to see number 11. I can enlarge that more if you want. It's quite similar to what we were just talking about. But what I like about this problem, everyone, it saved me time writing on this board, is they already got a vector field. So everyone see this vector field here? They got all these vectors. And they're talking about a path here. The path you got to take is from the point 1, 2, that's right there, to the point 3, 2. They go, could you explain why the line integral has the same value for all three curves? If you took a path like this, if you took a path like this, woo, 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 or if you took this path right here. And we go, how could we explain that? It must mean that vector field must be, starts with a C, conservative. So can we show that? That's how we're going to answer letter A. They want us to explain if this vector field is conservative, then it doesn't matter what path you would take to evaluate this. Where the curve, I'm talking about that C. It can be any one of those three curves. Or you and I can invent another one, a straight line. A fourth curve, right? Cool. So there's the vector field. What is it? 2xy comma x squared? All right, let me write it right here. 2xy is this conservative? I'm being honest, I don't know either. We just got to investigate. Once again, please feel free to ask me over and over, like, what do you mean by conservative vector field? The definition for a conservative vector field is this. That's the definition. For a vector field to be conservative, it means there's a vector function, potential function, where this is equal to the gradient of the function, which means it's made up of the partial derivatives. So the only way I can figure this out is, rather than going that way, we go this way. Now you can do it one way. You can do it like me. I was saying you could think of this as a question mark potential fx, and this is a question mark potential fy, and what would have to be true?
fxy equals fyx.
That's really what we're looking at. But the author writes this, you may prefer it. The author goes, just call this P, and call that Q. And he goes, check to see that dp dy equals dq. Yeah, it means the same thing. So either way I look at it. Now, is it true? What's the partial derivative with respect to an x of that? 2y. What's the partial of this right here with respect to the letter x? What's the derivative of that with respect to the letter x?
2x.
And this was 2xy. The derivative of that with respect to, whoops, I apologize. Look what I wrote. Let me do it again. What's the derivative of this right here? 2xy with respect to the letter y. 2x. And what's the derivative of this with respect to the letter, this right here with respect to the letter x?
2x.
2x. Does 2x equal 2x?
Uh-huh.
It sure does. Yes, this is conservative. And what does that mean? It means I can write this. Bingo. Now we've shown enough, we have enough information to answer letter A. We've explained it. What is the common value? Oh, they want us to evaluate it. So can we do that real quick? Wait, that means we gotta do a dot product and all that. We're like, no, all we gotta do is what? F of endpoint minus F initial point. But where's the F? We gotta find it. They didn't give it to us in the problem. We gotta go find it. Where's that? I'm talking about lowercase f, not this big F for vector field. So let's go find it, everyone. Where's that potential? We know this exists. I'm gonna write it down. This must exist. It doesn't always exist, but it does exist here if a vector field is conservative. All right, what's the now you get to integrate. What's the integral of that with respect to x?
X squared y. Right.
Yeah, because if you integrate that with respect to an x, you get 2x squared over 2, y. The 2's cancel and you get, now integrate that with respect to a y.
X square y.
Any repeats?
Yes.
I didn't want you to think you always get repeats, but the last 2 examples we got the what? The repeats, so we toss it. And there's your, all we're going to do is, to answer this question, I'm going to plug me in with the points are what? 3, 2, and 1, 2. That's all we got to do. I love this. So I'm going to write this down. It doesn't take much writing either. First of all, look what I did. I said you're that. And now, all I have to do is f of n point minus f of initial point. Hey, you can write it like it's written right here. You can write it like that if you want. So, there's f. And what's x squared y minus x squared y? Oh, they were nice this time. They give us the points. What were the points? 1, 2, and 3, 2. So when I need you to plug 1, 2, and 3, 2, just be careful. Where am I plugging the 1, 2, and where am I plugging the 3, 2?
3, 2 is the end point, right?
3, yeah, it went from 1, 2 to 3, 2. This was the point. So it started here and it ended there, the path. So plug in 3, 2, subtract, plug in 1, 2. Fundamental table line. So I'm going to need you to plug the point 3, 2 into that thing, and I need you to plug in a point 1, 2 into that. What do you get when you plug 3, 2 in there?
18 minus 2.
Yeah, so 2 squared is 4. 4 times 3 is what, 12?
No. 3 square.
Oh, 3 squared 9 and 2, 18.
18, yeah.
Minus
2.
2. What's the
16.
answer? And we'll go back. So we're saying that when you take this path right here, the work done by the vector field to move a particle along this curve would be 16. What if you took this path?
Same, right?
The work done by the vector field to move a particle from here all the way to would be 16. How about along this path? The work to move a particle from here along that curve to there